Welcome to the Deep Dive. Today, we're diving into a topic that feels like it's pulled straight from a sci-fi novel, but it's quickly becoming a foundational reality in engineering. How we're building the quantum future.
Yeah, and not just the hardware.
Exactly, not just the incredibly complex hardware. It's about incredibly clever virtual environments. We've sifted through a stack of fascinating sources, from cutting-edge technical papers to deeply visionary frameworks, to give you the essential insights on this.
It's true. Quantum computing promises extraordinary power, the ability to tackle problems classical computers can't even dream of, especially for things like complex molecular simulation.
But right now, there's a significant bottleneck preventing us from fully realizing that future.
And that bottleneck isn't just the inherent mind-bending complexity of quantum mechanics itself, it's also about the physical quantum hardware we have today, which is notoriously fragile and, well, incredibly noisy.
We're currently in what's called the NSQ era, the noisy intermediate scale quantum era. Current devices are limited in the number of qubits, they're susceptible to all sorts of environmental interference, and often many of those precious qubits are tied up in error correction rather than, actual computation.
Exactly. This makes designing quantum software remarkably difficult. Traditionally, it demands a deep, often inaccessible understanding of both abstract quantum principles and the nitty-gritty intricacies of the physical hardware.
It's a huge barrier.
This immense complexity slows progress dramatically and makes companies hesitant to invest heavily in software that might quickly become obsolete.
So if physical hardware is our shaky operating table, what's the steady surgical suite? That's where the central innovation comes in, the virtual quantum environment and something called the virtual quantic blueprint.
A simulation-first approach.
Right, a simulation-first approach. Our mission in this deep dive is to unpack how these virtual tools allow designers to bypass those physical hardware limitations, letting them create quantum software by simulating qubits in a controlled digital space. It's like gaining a programmable lens into quantum realities.
What's truly transformative here is how the Virtual Quantic Blueprint, or VQB, becomes a core of this entire design process. It's described as a dynamic digital map of quantum hardware.
Okay, dynamic, not just a static picture.
Exactly. Think of it not just as a static drawing or a fixed blueprint, but as a living model that allows for stage-by-stage manipulation while preserving the integrity of the quantum system.
A living model that instantly makes this concept so much more tangible. So what are the fundamental pieces that make up this dynamic map?
At its heart, the VQB is built on three core components. First, there are virtual qubits, which are digital entities with configurable states like the classic 0, low, 1 air, or those intriguing superpositions where they can be both simultaneously.
The quantum weirdness.
The quantum weirdness, exactly. Then we have states, which are the mathematical descriptions of these qubit configurations, often represented as vectors in Hilbert space.
Got it.
Finally, there are operations, which are the quantum gates and measurements that alter or observe these states.
Okay, so it's not just the individual pieces, but also how they relate to each other, right? I'm thinking about topology and ontology here. How does the VQB define the very being of these virtual qubits and their structural relationships?
That's a crucial distinction. Ontologically, it defines the being of virtual qubits with their specific quantum characteristics like superposition and entanglement, essentially, what they are in this digital world.
Their nature.
Their nature, yes. Topologically, it maps their structural relationships, such as how they connect and interact within a simulated circuit.
How they're laid out and linked.
Precisely. You can imagine the blueprint itself as a grid-like structure, with cells representing qubits and their states, all interconnected by operations that define the system's topological evolution. It's a dynamic template that maintains the core nature of the quantum system while enabling precise, step-by-step manipulation.
That analogy of a grid-like structure with interconnected cells makes so much sense. It's like a digital scaffolding for quantum computation. Now, let's walk through how this VQB mirrors the life cycle of a quantum computation, detailing those distinct stages of qubit manipulation.
Okay, so the first stage is initialization. Here, the blueprint precisely specifies the initial states of the virtual qubits.
Setting the starting line.
Exactly. This could be setting them all to 0 air, or perhaps putting them into a superposition using a Hadamard gate. It also defines the total number of qubits, their starting conditions, and any entanglement relationships from the outset.
Like pre-entangling them.
Yes. For instance, a blueprint might initialize 3 qubits into a Greenberger-Horn-Zeilinger, or GHZ state. This is a very specific, powerful way to entangle multiple qubits, allowing for highly correlated, complex experiments crucial for advanced quantum algorithms.
So once the stage is set, the qubits are ready for action. That brings us to the application of quantum gates.
Precisely. The blueprint then outlines the precise sequence and type of quantum gates, like Hadamard's CNOT or PolyX, applied to specific qubits. These gates are what manipulate the qubit states, creating superpositions, entanglement, or phase shifts,
The actual computation part.
all of which are critical for any quantum algorithm. For example, a blueprint might apply a Hadamard to qubit 1, then a CNOT between qubit 1 and 2 to create a Bell state, which is a fundamental entangled pair.
A classic entanglement. Okay. And after all those complex manipulations, you eventually need to get results, which leads us to the measurement stage.
Indeed, the blueprint details exactly when and how qubits are measured, which collapses their quantum states into classical bits, either a 0 or a 1.
Back to the normal world.
Back to something we can read easily, yes. It specifies how these outcomes are recorded and analyzed, often visualized as probability distributions. This step is where the computation is finalized and usable results are extracted from the quantum system.
So if you measure those entangled qubits,
If you measure one qubit after it's been entangled with another, for instance, you'd find their outcomes are perfectly correlated, reflecting their shared quantum state.
makes sense. And then, for even more sophisticated quantum algorithms, there are advanced manipulations.
Right, these cover more complex operations like multi-qubit entanglement that goes beyond simple Bell states, as well as error correction, or dynamic gate sequences needed for algorithms that create things like cluster states or implement quantum Fourier transforms.
More complex tools for more complex problems.
Exactly. Each stage, as we've discussed, is fundamentally described by a grid-like structure within the VQB, where cells represent qubits and their states, interconnected by operations that define the system's topological evolution.
Okay, so we're talking about designing entire quantum systems in a virtual world. But let's remember that these virtual manipulations are simulating incredibly real and often incredibly delicate physical processes. Why is that precise qubit manipulation so absolutely necessary in the physical world?
It all comes down to preserving their delicate superposition and entanglement. The main enemy in physical quantum computing is decoherence.
Ah, the noise we talked about.
Exactly. It's when qubits lose their quantum properties due to unwanted interactions with their environment. Precise control is essential to combat this.
How precise are we talking?
It's about having incredibly fine-tuned control over the qubit's environment and energy, like a master conductor guiding every note in an orchestra to prevent it from losing its delicate quantum properties.
And the virtual environments abstract all of that complex choreography away, which is truly remarkable. But what are some of those underlying physical techniques that these virtual blueprints are actually simulating?
There's quite a range that these systems model. We have quantum logic gates like PolyX, Hadamard, CNOT, and Toffoli, which are often visualized on the block sphere to show how they rotate a qubit state.
The basic building blocks.
Right. Then there's microwave pulse control, widely used in superconducting and spin qubits, and laser-based manipulation for trapped ions and neutral atoms, which precisely induces state transitions or entanglement.
And I imagine magnetic fields come into play too.
Absolutely. Magnetic field control is used in spin qubits to manipulate electron or nuclear spin states. And crucially, there are the quantum entanglement operations themselves, which create those profoundly correlated states vital for quantum algorithms.
Like the Bell states or GHZ states.
Exactly. IBM's research even suggests that strategically entangling qubits can effectively halve error rates during data classification experiments.
That's a massive improvement. Wow. What else are these virtual environments modeling?
We also have measurement and state collapse, where measuring a qubit collapses its superposition into a definite 0 or 1. Then there's flux control, a critical method for manipulating superconducting qubits by adjusting magnetic flux.
How does that work? Briefly.
Well, it tunes energy levels and significantly improves gate fidelity, though it does introduce vulnerability to flux noise.
So a powerful technique, but with its own unique challenges. Trade-offs.
Precisely. Always trade-offs.
Mm.
Other techniques include optical photon manipulation for photonic qubits, quantum error correction, often conceptualized as Peikin mode, in some advanced frameworks to fight decoherence,
We'll come back to that. Sounds interesting.
and measurement-based quantum computing, an alternative model where computation occurs through sequential measurements on a pre-entangled cluster state.
So these virtual quantum processors, or VQPUs, and simulators are truly bridging that gap, allowing quantum software development to proceed independently of the physical hardware we actually have in labs today.
That's the core innovation. These are powerful software applications that emulate quantum processor components within a classical computer's memory. They offer a practical and cost-effective way to develop quantum programs without being tied to specific physical hardware.
Get a head start on the software.
Exactly. This simulation-first approach enables rapid iteration and exploration of complex quantum AI interactions, without waiting for the slower development cycle of physical quantum computers. Companies like Daimler Truck AG and Volkswagen AG are already exploring quantum potential this way, for things like material science and traffic optimization.
That brings us to what I think is the most mind-bending part of this deep dive. Advanced frameworks that push beyond mere simulation to actually craft what our sources call programmable realities.
Yeah, this is where it gets really wild.
It's like computation isn't just a tool to produce an outcome, it's an act that defines what is real within its simulated universe. It suggests the programmer becomes a demiurge, a creator of worlds.
This is where these ambitious frameworks truly begin to redefine what we even mean by computation. One compelling example is Microsoft's Majorana 1 topological mapping of hardware, or M1TMH. This framework simulates a very specific kind of quantum hardware, Majorana-based qubits.
Majorana. What's special about them?
The breakthrough with these is their inherent fault tolerance. They encode information in a distributed, non-local way, making them incredibly robust against noise and decoherence.
So they're naturally jitter protected.
In a way, yes. Their information is almost like it's spread across multiple points, making it much harder to corrupt.
And it uses a fascinating symbolic system, right? Like abstract symbols to represent complex quantum operations.
That's right. M1TMH utilizes what they call a manipulations field of letters components. Imagine a kind of quantum alphabet where each symbol, like a Hebrew glyph, such as Aleph for initialization, Dagesh for state collapse, or Shva for phase shift, represents a complex quantum operation.
Wow.
This field is the interactive space where designers arrange and combine these symbols to program the virtual quantum system.
That's amazing. It's like designing with quantum hieroglyphs. And then there's the AI Genesis Engine and Higanling framework. This sounds even more visionary.
It absolutely is. This is described as a visionary, multi-layered AI framework that uniquely merges symbolic AI, mystical frameworks, specifically drawing from Kabbalistic traditions, like the 231 gates derived from Hebrew letter combinations, unity points, and Ikov Marbaya.
Kabbalah.
Really?
Yeah.
And topological quantum mechanics. Its quantum simulation and processing layer is designed to manage an astonishing 15,625 virtual Majorana 1 qubits.
15,000. That's an astonishing leap in scale. And how does a framework this complex handle all the inherent noise and chaos of a quantum environment?
It employs a unifying metaphor called coherent noise. This isn't just random static. It describes how the framework manages the probabilistic and noisy quantum environment in a structured way, much like a graphic designer uses controlled pseudo-randomness to create natural organic textures.
So managing noise rather than just fighting it.
Kind of, yeah. Within this framework, quantum error correction, or QEC, is conceptualized as tikkun mode, a Hebrew term for rectification or repair.
Ah, Tikkun mode again.
Right. It acts as a smoothing function that actively pushes back decoherence, constantly detecting and correcting errors to maintain system integrity.
And there's a whole concept called cubic entangling manipulation within this framework.
Yes. And this is where the ancient wisdom really blends with cutting-edge science. This involves arranging qubits in a cubic glyph lattice, where each vertex represents a qubit, and the edges define potential entanglement interactions.
Like a 3D grid for qubits.
Exactly. It leverages symbolic RLA-Shirem gates, which are 231 unique Hebrew digraphs. The Kabbalistic concept of Ikov Marbaya, or square folding, acts as a cubic boundary condition, requiring higher-order gates like Toffoli at the cube corners to maintain structural integrity and preserve entanglement.
This is pretty deep. It's a fascinating blend where ancient principles of structuring reality through symbolic combinations are applied to the very architecture of these quantum systems.
It's incredibly ambitious.
So we've got these incredibly ambitious frameworks. How do you design and manage entire new programming environments and AI reasoning models within this space? That's where the Quantum Linguistic Operating System, or QLOS, comes in, right? It's described as a meta framework.
It truly is. QLOS extends beyond simply simulating hardware. It's designed to create entire new programming environments, languages, and even AI reasoning models built on these quantum principles.
So it builds the tools to build the tools.
Essentially, yes. The blueprint concept in QLOS applies to the entire programmable material of any system being built.
Okay, let's unpack this a bit. QLOS has a hierarchical structure it calls degrees of design. What are these different layers?
At degree 0, we have the base reality layer. This is the physical equipment layer itself, the fundamental hardware, or potentially a very low-level simulation of it.
The ground floor.
Right. Moving up, degree 1 is the virtual lattice layer, which abstracts that physical hardware into a configurable virtual grid. This layer essentially defines the space-time fabric of the simulated system.
Okay, the abstract playing field. And then that fascinating symbolic aspect we talked about comes in at degree 2, I imagine.
Exactly. Degree 2 is the glyphic layer, where high-level quantum algorithms are defined by symbolic glyphs, encoding core quantum operations.
Like the Hebrew letters or other symbols?
Could be. Then, things get really interesting at degree 3, the runtime and adaptive design layer. Here, the system itself acts as a code designer. It analyzes its performance during simulation or execution and can suggest changes to the virtual quantum blueprint using AI-driven insights.
So the system optimizes itself.
Precisely. This means the blueprint is genuinely living, learning, and evolving.
A living, learning, and evolving blueprint. That's an astonishing leap. And finally, for us humans to interact with all this complexity, there's degree 4.
That's the prototype and user interface layer. This is the human interactive 3D visualization space. It displays the virtual lattice, qubit nodes, connections, and transformations, all overlaid with real-time data like heat maps for error probabilities, operational costs, and performance metrics.
So you can actually see what's going on.
Right. Think of the Rubik's Cube analogy. The basic mechanism enables incredibly complex computations to be discovered through its direct interactive use. This UI aims for something similar.
That real-time data and the interactive visualization must be absolutely critical for designers. Which brings us to our next point. Visualization itself. Why is visualization so important for this whole process? Not just for us, the human designers, but for the virtual systems themselves.
Visualization is critical for human intuition and also for the virtual systems themselves to understand what is happening. It transforms these incredibly abstract quantum concepts and manipulations into tangible and interactive models.
Making the invisible visible.
Exactly. This is essential given the complexity of quantum mechanics and the current limitations of physical quantum hardware. It's the gateway to true understanding and efficient design.
So what are some of the key techniques and tools that make this powerful visualization possible?
For a single qubit, the Bloch sphere is fundamental. It's a three-dimensional visual representation that clearly pictures its state, superposition, and phase.
The classic quantum visualization.
It is. For multiple qubits, circuit diagrams are essential for showing the computation flow and providing a topological view of their operations.
More like traditional schematics.
In a sense, yes. And I can imagine interactive simulators are an absolute must-have for developers working in this space.
Oh, definitely.
They are. Interactive real-time simulators allow developers to immediately tweak parameters, change gates, or adjust qubit states, and observe the effects, providing crucial feedback in building intuition. They often leverage virtual quantum processors, or VQPUs, for that rapid iteration we discussed.
And those amazing, almost artistic concepts we talked about earlier, like crystallographic glyphs and topology-preserving morphs, how do they visualize?
Crystallographic glyphs transform abstract mathematical symmetries, like those defining crystal structures, into tangible visual shapes, making complex symmetries visually graspable.
Seeing the symmetry.
Right. Topology-preserving morphs are advanced animations that smoothly morph underlying structures and glyphs while ensuring connections remain intact, allowing visual tracking of the system's evolution over time.
So you can watch how the structure changes but stays connected.
Oh, cool.
Yeah.
And in entanglement, how do you visualize something that's so inherently non-local and correlated?
Entanglement is often visualized as glowing, persistent links forming a dynamic 3D graph between qubits, making those abstract connections visible.
Like threads connecting them.
Pretty much. For quantum error correction, or Tikkun mode, it's presented as a 3D lattice with color-coded error anomalies actively corrected by stabilizer agents, visually representing decoherence as a fog that Tikkun mode actively pushes back.
Ah, seeing the fog of decoherence being cleared, that's powerful. What about those symbolic interactions we heard about earlier, like the manipulations field?
The manipulations field of letters components is an interactive layer where users can directly manipulate symbolic representations like Q1 for qubit 1, H for Hadamard, or those Hebrew glyphs we discussed. dragging and dropping quantum operations?
Something like that, yes. And observe their immediate effects on underlying quantum states and visualizations within a virtual grid, directly reflecting the topological structure. Even flux control changes in superconducting qubits can be modeled as 3D wave distortions around a qubit, giving designers an intuitive feel for those parameters.
And what's the underlying technology that brings all these complex visuals to life?
Three.js, a powerful JavaScript library, is integral for rendering abstract quantum concepts and manipulations into tangible, interactive 3D models.
So web tech powering quantum design.
It's used for everything from the block spheres to visualizing entanglement and error correction. And of course, the QLOS Degree 4 user interface is itself a comprehensive 3D visualization space, displaying all those real-time data overlays to give designers immediate rich feedback.
This is truly extraordinary. So what are the broader implications of this simulation-first and programmable realities approach? How will it transform industries beyond the quantum lab?
The transformative potential is immense. We're talking about revolutionary advancements in artificial intelligence, enabling advanced data pattern recognition and even hyper-realistic AI behaviors.
Better AI, faster.
Potentially. In drug development, it means simulating molecular-level quantum mechanics for incredibly precise drug discovery. It will revolutionize financial modeling with complex risk assessments and cybersecurity with robust post-quantum algorithms to counter future threats.
And real-world applications are already being actively explored, right? We mentioned a couple.
Absolutely. Companies like Daimler Truck AG are exploring quantum for materials science, like designing better batteries. Volkswagen AG is investigating it for highly complex traffic optimization problems in smart cities.
Better traffic flow. Yes, please.
And it could significantly improve weather forecasting and climate change modeling by analyzing incredibly complex systems with unprecedented accuracy.
Big, complex problems needing quantum power. Beyond the direct applications, this whole approach seems to be fundamentally redefining what we even mean by designing a computational system.
It does. It fundamentally redefines what we even mean by designing a computational system. By allowing the exploration of complex quantum and AI interactions without being constrained by current hardware limitations, it directly bypasses the noisy, restrictive nature of the NESQ era.
You're building the simulation and the thing being simulated?
In a way, yes. You're not just writing code, you're designing the very structure of computation itself from the ground up in a virtual universe.
And that leads us to the ultimate, profound philosophical provocation. As we get better at engineering these complex realities using virtual blueprints and symbolic frameworks, what new forms of intelligence, or maybe even what new kinds of realities, might we actually be constructing in the process?
This is precisely where the lines truly blur between simulation, design, and the creation of new realities. It's just that programming itself becomes an act of creation,
Like being a demiurge.
with profound ethical and philosophical considerations for what we are building and what might emerge from it.
So, to recap, we've explored how the urgent need to overcome the hardware gap of the NESQ era has driven us to develop virtual quantum blueprints.
These living, dynamic digital maps.
Right, composed of virtual qubits, states, and operations, allowing for stage-by-stage manipulation, mirroring the entire quantum computation lifecycle.
And we dived into the revolutionary advanced frameworks like Microsoft's M1TMH, the AI Genesis engine, and the quantum linguistic operating system,
But really mind-bending stuff.
which are not just simulating but striving to create programmable realities, blurring the lines between computation and ontology.
And throughout all of this, visualization is absolutely critical. From block spheres to glowing entanglement graphs, and the QLOS Degree 4 interface with its real-time data overlays.
It's the gateway to human intuition, and even for the virtual systems themselves, to understand what is happening within these new computational worlds.
This isn't just theoretical. It points to a future where you, the listener, could potentially be interacting with or even creating computational universes defined at their very foundation.
Shaping reality at a quantum level, virtually at first.
It really makes you wonder, doesn't it? As we dive deeper into designing these complex virtual realities, are we just building better computers, or are we beginning to understand and perhaps even define new forms of existence itself?